Okay, we'll let everybody sit down. Um, yeah, good evening. I'd like to welcome everybody on behalf of the Lamont-Doherty Earth Observatory to tonight's conversation, which is entitled Clearing the Air, Understanding New York City's Air Quality and Climate. So my name is Steve Goldstein. I'm the interim director of Lamont-Doherty Earth Observatory, and I'm a professor in the Department of Earth and Environmental Sciences here at Columbia. Our public lecture series, I hope that you've been here before, and if you haven't, I hope you come again. It's proud to feature distinguished Lamont researchers who work to uncover how the Earth works and identify the implications for both our local communities and the broader society. We've been around for over 74 years now, and the scientific insights Lamont generates has been fundamental in guiding impactful solutions for our society. And tonight I'm really proud to introduce our speaker, who is Professor Roisin Commain, and she's going to be talking about her important research on air quality. Roisin is an associate professor in the Department of Earth and Environmental Sciences here at Columbia, and a member of the Ocean and Climate Physics Division here at the observatory. As you'll probably notice, she hails from Ireland. She received a master's degree from Imperial College in London and her PhD from the University of Leeds. And before she joined our faculty, she was a postdoc and research scientist at Harvard. Roisin is an atmospheric chemist who uses observations and modeling to analyze the distribution of gases in the atmosphere and to investigate gas emissions from both natural and anthropogenic sources in cities and in remote areas. She works with New York State agencies to identify previously unidentified sources of methane, and she also works on developing pathways to reduce these emissions. Now, and she does good things for the area here. So I'm a resident of Spark Hill. And I met her in the parking lot one evening, like a year or two ago, and I clued her in on the Orangetown wastewater treatment plant, which we may know something about here. And where I live, it's a source of noxious fumes to my house when the wind blows in the wrong direction. And a few months later, she came back to me and she thanked me for telling her about it. And now she's doing something. She's monitoring it or something. And she told me it's being used in some kind of high-level state study on methane emissions, I think. But anyway, she can clarify or correct me about it. She knows the details, I don't. In any case, I'm sure her lecture tonight will be illuminating and engaging, and there will be time at the end for questions, so please hold any comments till then, and then she'll answer all your questions. And with that, please join me in welcoming Roisin to our stage.
Well, good evening. That makes me sound way more awesome than I think I am. So thank you all very much for joining. I'm excited to talk with you about some of the work we've been doing around New York. I'm not going to talk about Rockland Wastewater Treatment Plant because we're just beginning to start that. But yes, we're using it as a kind of a test bed to figure out what methods we should be using to reduce the methane emissions and hopefully the smell. So I'll come back in a year and let you know what worked and what didn't. How about that one? So instead, I'm going to talk today about understanding New York City's air quality, how that links in with their greenhouse gas emissions at the same time, and then what the global climate impacts are of some of these emissions as we start thinking about it. I've going to have a bunch of measurement stuff, so I like measuring gases. That's where I'm coming from on this, and trying to figure out, well, what are we actually seeing? So that's what I'm going to try and talk a bit about today. But some of the reason we worry most about the greenhouse gases is worrying about the global temperatures. So this is a simulation from the NASA GISS surface temperature simulations. And 2023 was by far the warmest year on record. And it really started through the summer, and it never really got as cold as it should have since. Now, most of that is driven by greenhouse gases. Now, we need greenhouse gases. The Earth would not have a livable climate if we did not have a greenhouse gas layer. We have a layer of gas around the Earth that allows sunlight to come in, and then heat would go straight back out to space again if there was no gas there. So we need some of that in order for the Earth to be warm enough for us to live. And the gases that we have in that layer are things like carbon dioxide, methane, nitrous oxide. These are what we call most of the greenhouse gases. There's a few others too, but this is what I'll talk about today. And that blanket that it provides around the Earth, it's very important. The problem becomes when that blanket is too thick. So it's like you putting on a quilt and suddenly it's summertime and you don't need as thick a layer as you think you do. So that's some of our problem, is we've got a massive increase in the amount of CO2 and methane and nitrous oxide that are not allowing some of that heat to go back out to space again. So it's trapping that inside. Now, we have some pretty long-term records, and then we have some very specific records of what the CO2 concentration is. Now, this is a time series from Mauna Loa, which is a volcano measurement site for the NOAA Observatory in Hawaii. And they measure CO2 there and have with scripts since about 1958, I believe. And they've been measuring there for quite a long time. Now, before we have these long-term time record, there are records going back further in time. And we were at about 270 parts per million. So that's 270 molecules of CO2 in every million molecules of air. So it's a very small amount, but it has a big impact. Now, in the 100 years before this record began, we increased by about 50 parts per million. Now, I don't know if you guys can see the numbers over here, but that is 320, that is 420. So we have more than 100 ppm increase in the last 60 years. So we are really accelerating how much. 50 ppm of that has happened since the year 2000. And it's really only when looking at these kind of time series we realize how much and how fast everything is increasing. So when we emit CO2 into the atmosphere, it lasts in the atmosphere for about 100 years, its atmospheric lifetime. And the CO2 is driving a lot of heat as we go, but most of the continuous growth, so I don't know if you can see, but there's a black line that goes up along through here that seems to be getting steeper and steeper. And all of that is coming from the CO2 that's produced when we burn fossil fuels. So I have a nice little car and a factory. You'll see them coming through. I think the car's cute. But what you can see on top is this red squiggle. So when they started measuring at Mauna Loa, Charles Keeling, they were measuring, they thought something was wrong in the 50s because the numbers started going down and they thought the CO2 was only going up. So it turns out that there's enough trees in the northern hemisphere to absorb CO2 that you can see it in Hawaii, and all the way through the summer the CO2 goes down. And then it comes back up again when those trees go to sleep in the winter. And it was the first time they weren't expecting to see the seesaw. And you can see every time, and it's not always the same seesaw. Most of the variability we see in those numbers in the atmosphere depend on how much have trees decided to grow, what have the conditions been like in any given summer. That is a big driver of how much variability we see in a lot of these signals. So we have plant uptake in the northern hemisphere. Summer is a lot of our drawdown. There's some respiration, so photosynthesis is when trees take up CO2. Respiration is when they give it back out, or soils will give out CO2 as well, and the oceans will also cycle. Now, it does mean that we end up with quite a large what we call an interhemispheric gradient. So if we're emitting all the CO2 in the northern hemisphere, how does that look when you look at it in the southern hemisphere? And I was involved in a pretty big project back from 2016 to 18, where we took this NASA DC-8 aircraft and flew it around the world 4 times. A lot of time zone changes, it was a lot of work, but we got some amazing detail that we did not have previously. So in this case, I'm looking here from the North Pole all the way to the South Pole, and it's like you're looking from the US towards Asia. So it's kind of looking that direction. And then we go up in altitude to about 10,000, 12,000 meters, so 40,000 feet type thing. And what you can see is we have an awful lot of CO2 kind of north of 15 degrees north. And this is in May, so it's in kind of late season. And we've emitted an awful lot of CO2 in this area. But that's not where we see the highest CO2. In fact, the highest CO2 we see is north of Anchorage. It's as we go towards the North Pole. And that's because the weather systems will push these long-lived gases around. And you'll end up with an awful lot of the pollutants in the very north. So I do a lot of work in the Arctic too. It's pretty depressing to see how much it's warming, how the ecosystems are reacting to that. Thinking about what is causing that is what got me to think about things in New York City a lot more. So this is a simulation by the NASA Goddard in Maryland. It's the GMAO, the Goddard Modeling and Assimilation Office. And they're running this simulation at an exceedingly high spatial resolution. And they have taken what we call inventories. So they have taken our best guess for what the CO2 emission would be from people, from the anthropogenic fossil fuel burning side. And then they've also included what we see for plants taking things up. And there's a number of different things you'll see here. So from a lot of the cities, you see a lot of CO2 emission. And it swirls around, and we see these weather patterns that move it across the world. So everything we emit in North America ends up in Europe. I'm Irish, as you can tell, so about 5 days after we've had really bad weather, it ends up in Ireland, usually. So they blame me for their weather. It's been raining a lot this year. But you can see how red, so all the red is where the really high CO2 is. And you can see it's built up through the summer. Now we're getting into May here. And you can see all of this, it's really building up in the northern hemisphere. We also have some other things going on. Do you see this pulsing? So we're starting to have, the Amazon is breathing. It's taking up CO2 and giving a little back out. And you can see that breath kind of in the daily cycle. So you need sunlight to take up CO2 in plants. A lot of it comes back out at night. So you see that cycle happen. Now what they also have imposed on this is what you see for carbon monoxide. So carbon monoxide, CO, is what happens when you don't completely burn something. And you'll see in the southern hemisphere here places where we have fires. And then in the northern hemisphere, when the fires start to kick off, the white you're seeing in the atmosphere is that CO moving through. So we're looking at August here. Most of the CO2 is gone. All the trees have taken up a huge amount of that CO2 that we emitted that year in the simulation. Now, you also see some fires. There's seasonal, naturally occurring fires in many different regions of the world. That contributes some CO2 as well. And I often like looking at just this time period where you start seeing everything is kind of back to what we think should be happening. You know, it's kind of all gone. We're starting to see the snow move south again as it starts getting cold in the winter. And then it's really easy to see how much CO2 comes off a big city and then rolls around the world. Now, there's some particular cities that jump out at me here, many in the US, but not only that. We see a lot of different regions have a lot of different emissions. And then as all the trees have gone to sleep, the CO2 builds back up again in the atmosphere. So that's the cycle we're looking at in that previous time series. We kind of see it moving all through. And the amount we're emitting each time, there's only so much trees can do for us. They have been bailing us out a huge amount. The oceans have been bailing us out a huge amount, but we're still emitting an awful lot of stuff. Now that's available online, highly recommend it. You can just like Google for that, or if anyone wants the link, let me know. Now, so the fossil fuel combustion, we had represented there just the CO2, but when you burn something, it's never just CO2. Not even the most pure fuel of any kind will just give you CO2 because nothing ever burns that well. What happens is we get other things produced at the same time, depending what you're burning or depending how you're burning it. So that's what we're going to talk a little about here. So if we look at cars, usually the only time you can see anything from a car is if it's particulate matter and something has gone horribly wrong. You shouldn't see anything coming out the engine. Now, we do get different behaviors, different gases coming out in different ratios, depending on whether we're looking at a petrol car, so I say petrol, unleaded, gasoline, regular, light-duty car, versus diesel. So those two are very different fuel types when you burn them. Diesel burns a lot hotter. So it will take nitrogen in the atmosphere. You've got two nitrogens. It's hot enough to split that bond. So the nitrogen will combine with oxygen and start making NO, nitrogen oxides. And it'll start moving through. You get a lot of NO, becomes NO2. That's really irritating for your eyes, your skin, breathing. If there's a lot of it, you'll really feel it. You'll have a lot more NOx with diesel because it burns hotter than you will with petrol. So the temperature of the combustion really matters there. You'll also get things like benzene, toluene, depending on what kind of diesel you're burning. Some diesel will have a lot of sulfur oxides, ends up forming acid rain. That's something we do worry about as well. The petrol is usually a little bit cleaner. It doesn't burn as hot, so you will have less NOx, but you will have something called carbon monoxide. So it's not burning as completely, so we get a different balance there. Now, if you have power plants, depending on what you're burning there, you can have a lot of different pollutants. If you're burning coal, there'll be a lot of chlorine, sulfur, mercury. All of those things are highly toxic to humans. If you've got something like oil, you'll have less of the toxic stuff, but it's still not great for you. Depends how much sulfur is in it, really. And then natural gas is kind of the cleanest of the fossil fuels. If you've got methane, it'll burn quite well if you're burning it correctly. And now keep that in mind. Natural gas is only a clean fuel if you burn it. I'm going to ask you all a pop quiz later who was paying attention to that one. So something we worry about is if all these CO2 emissions can be related to air quality, can we learn how to improve the air quality while also reducing our CO2 emissions? We have to reduce the CO2. From a climate perspective, we have to figure this out. How do we do it in a way that is healthy for all of us? So something we've been looking at a lot is thinking about, well, what have we learned so far? What worked and what didn't in times gone by? And here on this side, it's different sources of fuels and how much other things they emit alongside CO2. So we have petrol and diesel. If you were to move from petrol to diesel, what are the upsides? What are the downsides? Same thing for going from coal, that's supposed to be a piece of coal, to oil, to natural gas. What are the benefits and what are not? And then thinking about going from, if you've got an natural gas cook stove, should you move to something like wood? A lot of people are being told don't, by the way, before anyone gets any ideas. There's some marketing to say wood is better, it cooks, blah, blah, blah. It's a really bad idea. So, well, let's have a look at the why. There we go. So European policies, as part of Europe's push to make their Kyoto Protocol commitments, tax-wise in Europe, diesel became the favored vehicle. My parents in Ireland couldn't even buy a petrol car the last time they went to go buy something. So tax-wise, everything became diesel. Now, that meant that the NOx levels went up to the point where, okay, fair enough, some of the companies were lying about how much NOx each vehicle was producing, but we knew it was there. Everybody measuring in Europe knew it was there. The best we can guess is 32,000 people died because VW were lying about how much NOx was being emitted into the atmosphere. And that is a system of, if you're favoring diesel, it's going to have more pollution unless you figure out how to take that NOx out of there. So we've learned from that, maybe that wasn't the right idea. Now, why did they push for diesel? You can travel a lot further on a gallon of diesel than you can on a gallon of petrol. So from a CO2 perspective, it was the right call. But they didn't have an atmospheric chemist in the room to tell them no. And that's some of my major concerns into how I got into a lot of this was we need to have people talking about the air quality while we're talking about the climate impacts. So in that case, it was both NOx and PM, which actually hurt a lot of people health-wise. And then in Europe right now, there's a big push to favor wood burning because it's climate neutral. Because, oh, it's a tree we're burning, and that tree already took up CO2. I mean, it took up CO2 and has already bailed us out, so burning it now is not much help, is it? So I have many reasons to disagree with that policy. The big reason I have is how much particulate matter comes from wood burning. Now, as far as I can tell, the rules on wood burning stoves in Europe and the US are very different. If you can smell wood burning inside if you have a stove, that means the particulates are getting into you. It's quite dangerous. So it's the kind of thing I don't think we should ever be pushing, but I know there are places where it is the only fuel source. Fairbanks, for example, most people outside of the right in the city centre are burning wood as their only heat source. So we need to come up with better ways to do that, but at the same time, we shouldn't be encouraging it. So they were a couple of examples where making the air quality worse has killed people in the process while trying to make the CO2 go down. Now, can we come up with better ways to do that, where we reduce the CO2 and we make the air quality better? Now, one thing that I use a lot is thinking about all of these different emissions. Can we use this to fingerprint what we end up looking at in the atmosphere? So if something has, for example, a lot of CO, it means it wasn't burned very well. If something has a lot of methane and ethane, that's what we call thermogenic. So it's natural gas is the signal we're looking at. So all the different ways that the gases balance each other, we can use it to fingerprint what kind of sources we're looking at. So it's the same principle as thinking about that. Now, reducing carbon could lead to cleaner air, doesn't in all cases, but where's all the CO2 coming from? Now, I said a lot of it comes from cities. Where do you think is the largest city for CO2 emissions globally? Anyone, any guesses? Beijing? Where else? I'm hearing guesses here, yeah? New York, Shanghai, Beijing. Anything else? LA? Mexico. So these are all good calls. It's surprising what's not on this list. So on this side is how much does a metro area emit for CO2. On this side is how big is that city. So we have Hong Kong, Guangzhou, really big industrial city. I didn't hear anyone say it, but Seoul would not have been on my list. Given the population, New York was not third in the world on my list either. But the US has quite a few cities in the top 10. We also have cities like Tokyo that have a much larger population and yet have much, much less CO2 emissions. How do we get New York to Tokyo? That's something I am quite interested in figuring out. Don't know how we're quite going to get there, but people have ideas. So thinking about it, if we can figure out how to get some of these cities to reduce their emissions, it will make a massive dent in how much CO2 is being emitted into the atmosphere. So I started looking into, well, where's the power coming from in New York City and New York State? Because I was living in Massachusetts for about 10 years, and I always heard New York, they're so clean. It's all renewables, isn't it amazing? And it is on this site. If you only look at upstate, now it says upstate on the document they created, but I think it's pretty much anything north of Westchester. So it depends on where you're from, whether you agree with that. But 91% of the energy produced upstate is clean energy, as in it's not producing any CO2. We come down here, and it's 90% fossil fuel. So that's a really big difference. Now, upstate, the hydro is fantastic. Transmitting electricity that far is difficult. New York City has laws that require half of the energy used in the city to be produced in the city. So the city actually has a very good inventory for where it thinks the CO2 emissions are coming from. Now, I say inventory, it's our best guess of where we think the CO2 emissions are. New York has some of the best data I've ever seen on this. Most cities cannot afford to do this. I don't know of one other city I've ever worked in that has had the capability of putting this together. So I'm not knocking it at all. I'm just wondering have we got everything in there? Can we help? So if we think about it, we have residential over here, and most of the residential energy consumption is natural gas burning in homes. So you think about, I'm in a high-rise building that has a boiler in the basement and it provides forced air to every apartment in the building, or you have a 6-story building and you've got all the apartments on steam heat and there's a boiler in the basement, that kind of thing. Some are electrical. This is what the power plants, most of which burn natural gas too, but they're providing electricity. And then we have manufacturing, so that's the commercial and institutional, residential, and then manufacturing and construction. Now this is for 2017. We've done quite a good job with it. But what you'll notice is the part that I often just kind of gloss over, which is anything in gray in my head, I just kind of skip those. But there's a very interesting story with what's going on there. That was not always as small, those gray bits. That's residual fuel oil, so distillate fuel, whether it is bunker fuel, type 6, slightly less gunky, type 4, cleaner oil, type 2. I'm coming from somewhere like Europe banned bunker fuel for home heating decades ago. The stuff is so toxic, produces so much sulfur, particulate matter, acid rain. They've had to move away from that for decades. Never even occurred to me that a city like New York would be burning it until about 2012. And then the rules came in of maybe we shouldn't be burning bunker fuel in a city. Now this is so bad, it's not even burned at sea anymore as of January of 2020. So this is stuff we should never have been burning in cities. But what we have here is the sulfur dioxide measurements in Queen's College over in Queens. They have a very good measurement site there. It gives you a very good sample of the city. And they've been looking in the red here at, it was kind of dropping, and then the policy came in to take out bunker fuel, and suddenly it dropped way down, and we're looking at much lower numbers here. Now this is the wintertime average. And graduate student Yue Zhao pulled this out for me. We also had a site in Pinnacles, which is just south of Corning, if anyone knows the area. It's a remote site. It sees a lot of outflow from Pennsylvania, but it's pretty remote. And then Whiteface Mountain, which is kind of go towards Albany, keep going, and it's up that direction. So head for Canada. So it's pretty remote, way away from the city. And we're not quite down to what it is there, but we're at the cleanest New York has ever been from a sulfur perspective. So that's a really good thing. Particulate matter has changed, SO2 has dropped. That's really great. Now that was fully implemented by 2015. And it doesn't show here, but in the New Jersey data for similar stuff, we started seeing a bit of an increase. It turns out they finally increased the number of decimal places they were measuring or reporting. And suddenly it looked like a small increase, and it turns out it was not an increase at all. It was how many decimal places. If you've got 1 and 0 and it's just reporting 0.1 is suddenly an increase. So we learned our lesson on that. But what I couldn't get over, I thought, New York city was way behind. And then I started looking into it. I don't know if you can see the date on this. November of 2021, Hochul finally signs a law banning bunker fuel from being used in the state of New York. That was a bit later. This one is from March of 2023, which is talking about taking out grade 4 fuel oil in new builds. Anything that already is burning oil can burn it. Highly recommend moving to cleaner stuff if you could. But it does make a big difference then. So if that's our residential, this is the part we were thinking about most as residential combustion. The other stuff we were looking at was power plants. So 50% of the power in New York has to come within the city limits. And this is a paper from Cynthia Rosenzweig looking at what is susceptible to flooding, which I hadn't really thought much about. Chemist, don't really worry about water, but it is important. But you'll notice all these black dots are where we have power plants in New York City, all the way along the East River. The amount of money tied up in real estate for power plants in the city, I just think it's shocking. You can see some of these. So this is Ravenswood, which is if you get the Queensboro Bridge or the tram thingy to Roosevelt Island, you can see it just kind of there. Most of these were coal. And the reason I pulled out Ravenswood is they've left all the infrastructure in place. So you can see they'd load a barge right up to it, offload the coal into the plant, and then use that. So now they have moved to natural gas. The last coal-fired power plant in the state of New York closed in 2020. In my head, I thought it was way before that. But they're all now burning natural gas, so they are a lot cleaner. Not perfect, but they are a lot cleaner. So if we go back to this plot again, this is a really good estimate of where we think the power is coming from. But if we're thinking from a total CO2 emission perspective, what's missing from here? What would you normally think of as your CO2 emission in New York City, or your pollution emission in New York City? How do most of you get here? Cars. This is just the stationary. That's not thinking about cars, so we need to come back to cars. But also, if there's anything else in here, an inventory only includes it if we know we need to. So that's something to keep in mind. If something's missing, we won't have it in there. If we don't have quite the right number, we might not have the same thing in there either. So fugitive methane emissions, I'm going to kind of ruin the surprise and say that number's completely wrong. Just going to say it now. I'll come back to why in a minute, but it's a good best guess. It's just not right at all. But can we use something like the atmosphere measurements I make to be able to tell what we're missing? Can we tell processes that are missing? How much we're missing of things? That's the kind of question. So we have a number of field sites around the city. One of them is in Harlem, so it's on the Cooney building at 133rd and St. Nicholas. And it's got a really nice view. Like, we go up to the roof and look, that's St. Nicholas Park, Morningside Park, Central Park, and Midtown is kind of down that direction. So we get a pretty good fetch. If we go up on the roof and look out, LaGuardia is we're directly under the flight line, so no messing with anything tall. But there's little dots over here, that's the Astoria power plant, so we can see that too. And we can see all the way over to Randall's Island, Ward Island, that type of thing. And we use some of these very fancy instruments that are in the lab. This one is 200 pounds and a royal pain to try and move, because I'm not the tallest or strongest. These ones are a little easier, and it's getting to the stage now where we can use slightly smaller instruments that we put in the back of my Prius and drive around the streets to measure a bunch of stuff. So technology has come on pretty well in the last couple of years to allow us to do things. But I like measuring things in the atmosphere, because the atmosphere does not care what my opinion is. The atmosphere will take whatever you emit into it, mush it around, and then you measure the concentration. It's up to us to figure out, well, what is driving that? So we think a lot about, because I look at long-lived gases, CO2 lasts for a century, methane lasts for a decade, CO lasts a couple of months in the winter. So we worry about how much of a gas there is coming into the region, and we have a couple of background sites that we use for that. We worry a little about how the air is moving, and we can use atmospheric transport models to simulate, like, you can feel gusts moving around. Every time you feel a breeze, it's moving air around. You can't always see it. I highly recommend a bubble gun. Great, the little toys where you can shoot bubbles out and watch the eddies move. It's a great way of telling what's moving where. And then we can use the concentrations we measure in the atmosphere to figure out how much we emitted into the atmosphere in the first place. So all of these three things contribute to the concentration. So if we measure the concentration, we can flip it around. And the first thing we were looking at was thinking about biogenic CO2 in New York City. Would not have been the first thing I was thinking of. I was mainly aiming to say, okay, if we measure CO2, we can tell if that inventory is correct or not. And then I got here and realized that actually there's a lot of trees. It's nice, I love it in the summer, but that means we need to start figuring out where the trees are and how much, like you could see from a global scale, those trees breathe. They take in CO2, they give a bit back out. How do we include that? So we started looking at, well, who else has come up with estimates for what that would be? And in this case, all the yellow means no CO2 uptake by trees. And most models pretty much say that there's no trees in New York City. Now, I've seen them. I know there's more than a few. But pretty much every model said there's nothing there because they were using such a coarse resolution, they couldn't see individual trees, or they couldn't tell. They could just say it's Manhattan. There's no trees. So if we're very careful, this one was a 12-kilometer simulation. This was a 2-kilometer simulation. And postdoc Dan Wei went and took a 30-meter land cover map and looked at all of this data here. So the high density is the dark purple, means it's very high density population. So you can see, most of Manhattan. If we take a zoomed in part of Prospect Park here, there's a 15-centimeter LiDAR map that New York City have. It's the only city in the world I know that has this. You can take that information and spot where every tree is, where every shrub is, where all the grasses are. It's phenomenal. And that resource available to researchers is amazing. So in this case, the pink are the buildings, the purple is the sidewalk, the gray is the road, and then you can see different types of green. So we have trees and grasses. And in this case, when you're walking along the street, you see some trees. They provide shade. I'm all for trees. What you're missing is most of them are actually in the backyards. So those trees are taking up a lot of CO2. Now, some of them are shaded. Some of them are heat stressed. Some of them are deprived of water. All of these things will affect how much they take up CO2. And we're trying our best at the moment to try and understand those behaviors a lot more. But we said we'd take a first look and see, well, if they behaved like a tree here at Lamont, what would they do? And that's what we've been looking at. So Dan went and looked at if it was a grassland, how much CO2 would it take up? If it was a forest, how much CO2? And then this is what, if there was no vegetation, in the places where we had previously not been able to see anything, you only put the trees in the big parks, what would you see? And there's a very big difference in the amount of CO2 that you would take up from that. Now, we were able to then use our atmospheric transport model and observations from some NIST measurement sites. This was before we started measuring a lot of things in the area. And using a site in northern New Jersey and a site in Mineola, so on the Queens-Nassau border, we were able to look at the CO2 difference in that with a transport model and look to see how much CO2 enhancement, how much CO2 concentration should we expect to see through a simulation for all of July for 2018. So here we have the mean CO2 enhancement. So we have a certain amount of CO2 coming into the area. We should see an increase in CO2 if we're emitting from fossil fuels. We should see the trees taking some up. And what we find is we have power industry, combustion, and energy for buildings are 3 different sectors, and each one of them overwhelms everything else. First thing I thought of New York was traffic. It's that tiny little orange line in here. So yes, it's massive by any other city's standards. It is tiny by New York standards. And that to me was really surprising. So if we take our simulation and we look to see, okay, how much CO2 are trees taking up in New York City? We find that it takes up quite a lot. We see it coming out at night when the trees are respiring. And then we see it going into the trees during the day. And we can see that there's kind of a cycle that goes with that. So we find that about 20 to 40%, depending, there's a pretty big uncertainty we need to figure out more of how to reduce that. But those trees take up quite a large chunk, about 1/3 of the emissions that we give out in a July day. And it's enough to actually account for all of the traffic. That to me was surprising. There's enough trees in New York City, there's 1 million trees here, that it's enough to take up the CO2 from traffic in the afternoon. Doesn't take it up at night. So it's very much a when are you talking about? Trees are fantastic afternoons and summers. And they are storing carbon, so that's pretty good. So we included the tree part of this, because if we didn't, we would have turned around and said the city is over-reporting their anthropogenic emissions, the amount of CO2 they're emitting from fossil fuels. I would have said it was too high. As soon as we started including the trees, it's spot on. Within noise, within uncertainty, needs to be done on a way more like many-year basis. But it's surprising how good that inventory is for CO2. I'm really impressed with it. But it did get us thinking about, we need to have the biogenic, so the trees and the people. So the biogenic are the trees part. Anthropogenic is what we call the human influence part. But it also affects air quality, what kind of tree you have. So, what do you think most trees in New York are? Anyone got any guesses? Ginkgo at my house. Yeah, no, unfortunately not, thankfully not. Anyone else? Yeah, okay, anyone else? Oaks. So, about half of what we see in the parks, now not on the streets, but about half of what we see in the parks are oak and sweet gum. They are 2 species of trees that give off a lot of what we call isoprene. So anytime you can smell a tree, That's a chemical species. We call them volatile organic compounds. It's a whole suite of everything you can think of. The magnolia smell as you came in, my favorite smell, so I'm biased towards it. But that's a VOC. So all the nice things you can smell about trees, all of those can react if they're put in the wrong conditions. The wrong conditions are the amount of NOx coming out of cars in cities. So if we're going to increase the amount of trees, it matters which kind of tree we then plant. So as we start looking at trees as a mitigation and adaptation, they are fantastic for helping to mitigate, say, urban heat island effects. Cities are just too hot when there's asphalt and everything else. It absorbs heat and keeps it. The tree provides shade. It helps cool things down a lot. Trees are fantastic for that. But which type of tree we plant does actually matter. So if we look at here, most of the estimates that were done before this were like, well, there's no trees, so there's no isoprene. Ta-da! And I was like, actually? So if we start digging into it, there are a lot of trees, and a lot of them that will give out isoprene. So Dan's been doing some atmospheric chemistry simulations to see how much ozone would that produce if we were to increase the number of the wrong type of trees. So she's been looking at if we planted another 1 million trees, and she went into detail about where could we plant them. There's only so many places you can plant trees in New York. Looking at additional tree cover with oak, you know, which of the boroughs could we put it in? There's an awful lot could go in Queens. We could even do a bit in Manhattan. But what we plant is actually quite important. So, and I'm going to come back to it in a second, but this is what we're at right now. And if we were to increase, we'd have to go down a factor of 5 on the NOx, not to make the ozone worse as we plant those trees. So trying to figure out what's the balance there. We need to reduce the NOx, but this line here is what happened during COVID. Took all the cars off the roads. We only got to here. So the scale of what's needed in this is quite big. So I'm trying to convince people we shouldn't be planting oaks, even though they are one of the most climate resilient. They survive in ways that other trees do not. But if they're giving off isoprene, which they do when they're stressed because they're hot, then it becomes an issue. Now, we've been measuring air quality in Harlem, and this is looking at the carbon monoxide. So if you only half burn whatever fuel you're looking at, you'll make a lot of CO. And this is looking at over a number of different years. Now, you'll notice that they're January to June, because I was doing this on the cheap, and I usually had funding to do something in the summer. So all the instruments would go back to Harlem, and we'd measure from before Christmas back out till the students needed to go do something again. So that became our, now we have a permanent measurement there thanks to NYSERDA. But this is looking at the stuff that was a bit more transient. So we had 2019, we were seeing way more. The black is what we observe in the CO. The red is what all the inventories tell us the CO should be. Now, for CO2, we were really surprisingly good. For the CO, we need an awful lot more CO in the city to explain what we're seeing. And same again in 2020, January, February, not so much, March, April. This is a bit of a mess. Anyone remember what was happening 4 years ago? So a big change. We had one of the largest experiments in the world for changing our emissions. Now, I know there was a lot of other things going on, but I was spending a lot of time trying to keep these things running, so I wanted to see what was happening. So during COVID, most of the buildings, businesses started to shut down about March 10th. The Friday was Friday the 13th. The kids all went home for spring break. Columbia never came back. CUNY never came back. Most of those kids were mailed their stuff. Hard way to graduate. Now, the mobility was down about 80% on public transit, about 60% traffic reduction at its peak. Now, that is probably an overestimate because we're using things like mobility indicators from, say, Apple Maps or Google Maps type thing. There was so little traffic, people didn't bother putting on maps. They could follow a route they knew and they weren't going to hit traffic. So it's probably not quite that much, but the roads were a lot quieter. And what we saw was a 40% drop in the CO, the NO2, the NOx, like all of the stuff you would assume was related to traffic, including benzene and all these other kind of things. But thanks to some very lucky weather, it was actually, we saw a bigger drop than we should have. The emissions only dropped 20%. Now, in my head, all those traffic emissions should have gone to practically nothing, but they didn't. They reduced a chunk, but that means we really are missing where is the CO coming from. And that's been something that's really bothered me for quite a while, because how do you possibly get this much CO? Carbon monoxide. You go to high concentrations, it will kill people. The CO is one of those, if you have a generator indoors and you don't ventilate it, people die every year from that. So you don't want that to be high. So here what we're looking at is the black is the CO again, and the red is what the methane looks like at the same time. Now, all known sources of methane involve leaks on streets. Now, not all, but until we were doing this, most of the methane was coming from leaks on streets, where you have never burned it. And there is zero reason in the world why methane and CO would be correlated like this. Now, it's not perfect. There's times when the methane goes up and I'm looking going, really? But there's an awful lot of similar stuff happening here that had me quite worried about it. So we've done a lot more digging into that. We've gone to Brookhaven National Lab and tested out boilers. We've been doing a whole bunch of stuff, trying to write it up at the moment. But the summary part of it is there's an awful lot more methane from incomplete combustion than we thought should be there. So that means people are buying methane, natural gas, they're paying for it, and then they're pouring half of it out their chimney without ever getting the benefit of it. But it also means it's not Con Ed's problem, which I hate to admit, but they think it's funny that I'm willing to. So it's the kind of thing we can use these different chemicals that we see in the atmosphere to try and pinpoint what is driving what we're seeing in a regional scale. So being able to measure methane and ethane quite accurately is really useful for that. We know it then it's natural gas. If we have the CO, we know that we're combusting it. The post-meter emissions, we're going to have to figure that out. Who fixes it? It's going to be a good question. So for our conclusions, greenhouse gas mitigation in cities, it can improve air quality if we're careful how we do it. We need to have the right people in the room to help make those decisions. Planting the wrong type of tree could make things a lot worse. So if you hear of your town promoting oak planting, please have someone check and see is that a good idea or not, because it does depend. It might be a great idea if your NOx levels are low. We need to include biogenic CO2. So if we don't include the trees in a city, we are going to be underestimating how much is coming from the people. If trees matter in New York City, they matter everywhere, because we've got so many buildings and so much emission. If it matters here, it really does matter. Someone asked me the other day about the electric car fleet. I'm like, well, COVID didn't make much of a difference when we got half the cars off the road. I don't think from an atmospheric chemistry perspective, it's going to have the impact that I was hoping. Somebody else made the point that it depends how we power them. If we're not going to make an effort to make sure our power is clean, we could be in trouble. A discussion to have. And then incomplete combustion, where you have this high carbon monoxide, it could be related to natural gas. We need to dig into it a bit more. Who fixes it? That becomes the big question. If we want to reduce the methane, it's not there on the streets. I've tried. Believe me, I've spent too many hours in my Prius driving the streets in New York. There's not as much methane as I thought there would be. So thank you for your time. I have a great group of students. Many of them are summer students that spend some time with us, and I have a number of great graduate students and postdocs I work with. And thanks to funding from NYSERDA, NOAA, and the CEJA Foundation, Alta Futures. So that has been great to get a lot of this going, but there's still a lot more work to do. So thank you very much for your time. Okay, do we have questions? And if you do, can we get you a microphone? Because I know there's people relying on the link to the, okay, one at the back. And then.
Thank you. Hi.
Hello.
There was one slide that you had that compared North Jersey to Queens, and the three major sources of emissions were combustion, power, and I forget what the third one was.
Industrial something, yep.
What is the difference between power and combustion, power industry and combustion in this slide?
From
here?
a chemical perspective, nothing. So they kind of look the exact same thing. Who is running them is how we think about it. So if it's a power plant, that's different from home combustion. So if somebody has a boiler in their basement, that's what we have classified under combustion if it's for water heaters and that kind of thing. So it's a bit arbitrary for some of the inventories, what we classify things as. I don't always fully understand it myself. Okay. So yeah, it can be quite arbitrary. It also depends which inventory you're looking at. This is EDGAR, so it's a global database of what we think the CO2 emissions are, and we wanted to know, people have been using it for a lot of things, was it accurate? I don't know if its attribution of everything was accurate, but its total number it was giving us at the end was correct. I'm not sure I trust as much like power and combustion, and I mean, they all sound the same to me, but they're three equally massive signals. So,
okay.
Yeah.
Thank you.
No problem. Hello.
Yeah, I'd like to just raise a point about planting the wrong kind of trees.
Yes.
Which is, as some of the people in the audience know, I'm a gardener and horticulturist. And I've been doing a lot of learning in recent years about plants, what kind of plants best serve the ecosystem. And one of the real leading figures in that is Douglas Tallamy, who's an entomologist at the University of Delaware, who's addressed the issue of the collapse in populations of insects and also birds. And of course, the birds depend on the insects, particularly on butterflies and moths, caterpillars, to feed their chicks. And he has come out very strongly in favor of planting oaks, because he says that oaks support far more butterflies and moths than almost any other kind of native tree. And how does that figure in? I mean, I see your point.
Yes.
But then he's also talking about the collapse of ecosystems in North America. And he's calling very strongly for planting oaks.
So can I ask your opinion? What are the ecosystems in Lower Manhattan?
Actually, you know, there's been some really interesting work done.
Okay.
For instance, not in Lower Manhattan, but right across the East River in Brooklyn Bridge Park, where they've been doing where they created some initially artificially supported ecosystems,
that
but
are now
has
maintaining
all kinds of insects and birds that hadn't been seen for many, many years.
Great.
Are reappearing, and it's become a rich place for the ecosystem.
Well, surprisingly enough, you can actually, from space, looking at the satellite images of NO2, you can spot the Hudson. You can spot the East River. So if you manage to plant them in areas without the high NOx, if they're in strips near the water, you can get away with an awful lot. I think it's having the discussion more of, if it's an area that we know has really high NOx, pick another tree. Now, most of them won't survive. We pick oak because it is one of the most climate resilient trees we have. Are there other options? I'm not an ecologist, but like there are certain options that are almost there. A maple, if it will survive, will provide a lot of biodiversity and doesn't give off isoprene. Gives off other things, but they don't have quite the same reaction. So I think, yeah, it's a great idea, and have that conversation.
Well, thank you for that enlightening presentation. I'm breathing a little easier based on your data. New York City is about to institute congestion pricing, probably in June. To what extent do you think that will lower CO2, particulates, and NOx?
And drive up the ozone.
Yeah.
So New York City has a little donut of where the ozone is actually really low in the city center because the NOx is so high. When you have NOx at an exceedingly high level, it'll eat up the ozone. We call it ozone titration. As we start to reduce that, we're actually going to make the ozone go up a little before it goes down. Now, the NOx itself is toxic, so we have to reduce it. But there's going to be a bit of a delay in how that effect kicks in, and figuring out how well do we measure that. It's a really good question. I don't know if we know enough to say definitively. I mean, if there's less CO2 emission and less NOx emission, that's a good thing in my book. How it's going to balance, I don't know. I think it's going to make things quite interesting. I'm living kind of just north of one of those lines, and you know, is my neighborhood going to become completely unlivable with everybody trying to park? There's no street parking anyway, so don't bother coming to Harlem. But it's kind of how it's going to affect things, I think it's going to be unexpected, I think. So I think our current models are not quite there for figuring it out.
Hi, I have a question about cities in general.
Mm-hmm.
If a city is in a warm place in the south, let's say, and they're burning dirty fuel, let's say coal, how would they read the same as a place like New York, who's doing more of the green thing, but it's cold more of the year?
Yes. So some of that will depend how much is it raining. Because a lot of the time, I mean, my parents' village in Ireland had some of the worst air quality in the world for a couple of days in February of last year, because it's in a bowl and how the air mixes, nothing was mixing, everyone was burning coal and wood, and it had some horrifically bad air quality. It has been pouring rain since last summer. They've got great air quality. So it depends. You can wash out an awful lot of the pollutants. So I'd look at it more of how frequently do you have precipitation events as much as anything. There is a temperature dependence if you have things like NOx and sulfate reacting together, if there's any ammonia at all, which we are now getting from like diesel emissions. And anywhere that's kind of in an agricultural area, you'll have a lot of that. Those, how much is in a gas and how much is in particulate form, that's very temperature dependent. So in hot areas, it'll always stay as a gas. As it gets colder, it'll form particles, and that's the stuff that is kind of more dangerous. So it depends on where you are. Most of it will be gas form. Most of it will rain out. The warmer it is, usually the more water that's in the atmosphere, the less it'll affect you. So there's pluses and minuses. We have a habit of burning more here in the winter when we are cold, but it is much more energy consuming to try and cool a building. It takes much more energy to cool buildings than it does to warm them. And that's going to be the big question of, as climate gets warmer, how are we going to deal with that? How are we going to keep these buildings cool? And how are we going to insulate them enough and not cause indoor air quality problems? Promise not to make anyone scared, so I'm not going to go there.
Thank you. Do you know of any plant material that does absorb the NOx?
That is a good question. So catalytic converters absorb NOx in cars. So the platinum catalyst in that works. I don't know of many, like if you have I'm going to go there. If you have a gas stove indoors and you only have a carbon filter, you're not removing any of the toxic gases. You're just removing the particulate matter. You have to be able to ventilate that outdoors. Most of the scrubbers are really expensive, so we put them on power plants. We put them in cars till they're stolen. I keep getting ads about mine is likely to be stolen. But it's an expensive process to take NOx out of things, yeah. Any other questions? And if anyone does have a gas stove, please make sure you ventilate.
Thank you for the talk. That was very enlightening, especially the combination of all the different gases.
Mm-hmm.
So you're looking at it locally,
Yes.
right? And there's some sort of ideal mix, right? And I'm not sure where you're at with putting all of those pieces together, but then there's also, right, there's the whole atmosphere, and like, how do you, I mean, I find it overwhelming to think about. You know, we all know about CO2, we all know about methane, and then it becomes a lot more fuzzy.
Well, a lot of the other gases don't live as long, which means they don't go as far. So for CO2 and methane, it'll move around the world. For NOx, it only lasts that day. It'll be gone. So as the wind blows it away from New York, it'll hit Connecticut, ozone will get produced, it may hit Maine. That's kind of as far as it goes. So it does depend on the atmospheric lifetime and what kind of, the more reactive something is, the further the smaller the distance it can go. So we start losing things quite quickly. So if you kind of think about how things move away, it's only the greenhouse gases really that get left to go the whole way around the world. Nothing else does that. So you can look at local behavior quite easily because you've got these other chemicals that are quite short-lived. So they just don't last as long. So we kind of split it up as short-lived and long-lived gases rather than thinking of them as air quality and greenhouse gas, because we're thinking more about how far is it going to go? How far away from us do we have to get a background concentration for it? So for something like methane, we're just seeing so much of it in the city that it becomes easy to define. Like we drive in from here, and the minute you cross the GW bridge, it just like you're looking at a signal, whoop, we're in Manhattan, like a step change. So it's kind of an interesting, it depends on the gas somewhat, but for most, even the long-lived ones, it's like step change as soon as you're across the GW bridge.
Okay, I think we'll have this one more question, and then I have a question.
You didn't comment anything about the fact that in New York State, gas stoves and ovens are being banned in the next few years. How does that affect the chart behind you?
So ovens are worse than stoves, but they still consume a tiny fraction compared to boilers. Now, I have a personal thing about burning anything indoors without proper ventilation, because it will kill people. It will give kids asthma. It is the worst thing you can do. And as we try and make buildings more energy efficient, ventilation is going to become more of a problem. We have to be able to get those pollutants out of there, or it will kill more people. So figuring out how to balance that's important, but it's really the boilers. Like your oven will use some natural gas, but if you're pouring it out of the boiler, that's a much bigger, you use way more natural gas in a boiler. So figuring out how to make them efficient and make them cost effective, I think is going to be something we have to do more. We should not be, it's a complete waste of money. I should not be seeing that methane at rooftops in New York. It's somebody paid for that already. And it just seems ridiculous that it's been poured into the atmosphere to warm things. So I don't know how we're going to deal with that. I don't think we should have gas stoves indoors unless they are very well ventilated. And there's no apartment in New York City that's well ventilated, mine included. So I'm okay with that one. Figuring out how to make it cost effective for boilers, I think, is going to be what do we do instead? Have we got ways of heating and cooling that make sense?
Okay, so I'd like to ask a question that's a little bit different. And so you've said a lot of things tonight that to me are, not what I would have thought were non-intuitive.
Yes.
And I'm just kind of wondering, so last year or last summer we had all those issues with the forest fires that were happening up in Canada, and it brought all kinds of stuff into the atmosphere of New York.
Yep.
Can you say a couple of things about the impacts of that?
Sure. I was actually at Croton Point landfill, the park up there. We do some work on the landfill. It's kind of the best operated landfill I know of in the area. Highly recommended as a park. And we were there not expecting to see anything, and suddenly the sky turned this weird shade of orange coming across the Tappan Zee. It was like apocalypse. There was nothing to be seen. We weren't expecting, those layers were passing over all summer. It was only when the wind brought it down to us that it became a health risk. And I ended up talking to a bunch of people about it. And the one piece of advice I had was close all the windows. You do not need to be breathing this. It's high particulate matter. We worry about that because it enters your circulatory system. It can cause strokes, heart attacks. The number of strokes and heart attacks after events like that goes way up for about a week. So going out and exercising in it is the worst thing you can do. So I was trying to be careful and warn people about that. So I suggested people close the windows. And if you have a gas stove, don't use it. And people looked at me like I was crazy. It was like, you've a microwave, use it. Take a day or two. So I think as more of those fires, we're seeing more fires in the Arctic. I do a lot of work there. The zombie fires so what burned last year in Alaska and northern Canada, a lot of it didn't go out. They're still seeing puffs of it happening now. They call them zombie fires because the peat can sustain fires over the winter under the snow cover. So those fires are beginning to kick off already, which means it's going to be some hell of a fire year again. So we're probably likely to see those events come down to us. It's just a trick of the weather. So the water has been so warm in the Atlantic that weather patterns have been all weird. So we could very likely see a lot more of those again next summer. So keep your COVID masks. This is what they're really good for. They're PM 2.5. You want to be filtering this stuff out. Try not to breathe it.
Okay, I'm glad I asked that question.
No, you're not. I just scare people.
Okay, well, in any case, I'd like to have everybody thank Roisin one more time. Okay. I just want to note that these lectures are voluntary, and Roisin basically this is a voluntary presentation by her, so thank you for that too, being willing to do that. Okay. I want to also thank the audience for coming here this evening. We're grateful that you're showing your interest, and we look forward to continuing the conversation. The public lecture series will continue in the fall, and we're excited to welcome everyone back then. This is April. April is Earth Month. I like to think that at Lamont, every month is Earth Month and every day is Earth Day. It turns out that next year we are having our 75th anniversary. It's going to be the 75th anniversary of Lamont. And we are going to celebrate throughout the year. So look out for outreach activities. We're going to actually put a lot of effort into outreaching to the general public. Among our scientists, many discoveries over these 75 years. We were the first to map the seafloor. We played a major role in the development of the theory of plate tectonics. And there are some people who are here who were here during that time. And we were also the first to reveal the ocean's role in triggering abrupt climate change. Your support can help us with our next big scientific discovery. So I just want to say before we leave, please consider supporting our work by making a gift to the Lamont Observatory during this Earth Month. And thank you for coming, and we'll see you soon. Thank you.